Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. In this video, I'm going to talk about the arc length formula that you will encounter in your Calc 2 course. And let me kind of set up the scenario. What I have is the graph of a curve, and we generally assume that it's not a straight line because those are easy to find the length of. But let's say I've got just some random graph here, and this is the function, say y equal to f of x, and we're looking at the interval from, let's say, a to b. And if I want to compute the length of this, how can we do that? Well, what I'm going to do is approximate this first and foremost. I'm going to come up with a formula for an approximation, and then we're going to then take a limit. Now, if you remember the definition of a derivative, we start with an approximation, say like the slope of a secant line, we take the limit, and then we get the derivative, which is the slope of the tangent line. For an indefinite integral, we start with a Riemann sum, which is just an approximation using rectangles. So it's like this discrete approximation, and then we take a limit and we come up with the definite integral. Well, we're going to do the same thing here. So let me redraw this so I can do it bigger. Actually, let me clean this up here so I can use the whiteboard space, or the glass space here. So let me go ahead and redraw a graph of this, and let's do it bigger. So let's say I've got this curve, and again, this is the graph of f of x on the interval from a to b. Okay, so let's say if we go from a to b. All right. As I mentioned, if the graph happened to be a straight line, those are very easy to compute lengths of. Therefore, I will approximate this by finitely many straight line segments. So let's say I go from here to, I'm going to do a different color, blue. Let's say I go from here to here, and then I'll go from there to, what I want to do is essentially approximate it with equal length subintervals here. So let's say this is, x1, where this would be, say, x0. And then I'll go over to x2, which is, say, be about here. And then if I go x3, and then I'm just going to, make it up here so where it works there to, say, there to there, and then there to there. Okay. So again, I've approximated the curve with straight line segments. So therefore, the arc length would be approximately the sum of the, I'll just abbreviate this as the sum of the line segments. Okay. Now what we need to do is let's come up with more of a formal expression for the length of one of these line segments. So let me kind of go ahead and take, say, this portion of the graph here, and let's zoom in on that. So if I was to zoom in on that, let me redraw this over here. And I'm just going to focus on that first portion. So say a to x1, where the original graph, say, looks like that, right? I've got a curve, and then the straight line segment is going to go from here to, say, here. Okay. Now, we want the distance on the x-axis. I will call this the change in x. And so that would be this portion right here would be the change in x. And then also this portion right here would be the change in y. And ultimately what I'm looking for is the length L. Okay. Now, how is the length L related to those two things? Well, of course, this represents a right triangle. Therefore, I know that the square of the length is the sum of the squares of the sides, and therefore the length is going to be the square root of the change in x squared plus the change in y squared. And this right here represents the length of any one of these little segments. And of course, y just represents the function f of x. So what I'm going to do is, let's take this generic concept for the formula and let's fill in a little bit more detail. The arc length now is approximately the sum. Well, what I found for the line segments was the square root of the change in x squared plus the change in y squared. Okay. Now what I'm going to do is I'm going to clean this side up, and we're going to then work with this, because I want to create a formula for the exact arc length using this approximation. Well, first and foremost, let me manipulate this expression, and I'm going to manipulate it as follows. So arc length is approximately the sum, again, of each line segment. What I'm going to do is I'm going to take this delta x squared and factor it out of the square root. First and foremost, I will write this as the square root of, so delta x squared multiplied by, well, if I factor it out, this would just be a 1, and then I would have change in y squared over change in x squared. Again, that's all under the radical. Okay. Now, I've got the square root of a product, so that would be the product of the square root, so this would be exactly equal to, again, these are approximate, but this right here, going from here to here, would be exact. The sum, the square root of the square, generally speaking, right, when we do a square root of a square, it's going to be the absolute value, and I'll reference that in here in a moment, how I can simplify that. And then underneath the radical, I would have the square root of 1 plus. Now notice this is the square of the change in y, square of the change in x, so just using properties of exponents, I will square the whole thing. I've got squared delta y over delta x, and that's still underneath the radical. All right. Well, delta x was a distance. Distances are always non-negative. In this case, we're actually going to be strictly positive. But in particular, I can just drop the absolute value bars. And since this is being multiplied, I'm just going to move this on the end. So this would be the sum of the square root of 1 plus delta y over delta x squared delta x. And again, this is approximately equal to the arc length. Now, in order to make, and again, this was just representing one of those line segments on the rest of that curve. If I wanted to make this exact, or let's just say increase the approximation, make the approximation better, we would take this delta x, we would take this getting smaller and smaller. So therefore, this curve would be represented by smaller and smaller straight line segments, which as delta x approaches 0 will give me the exact arc length, and therefore we have the arc length is equal to the limit as delta x approaches 0 of the expression above. Okay. And just clean this up right here. Now, this is the limit as delta x goes to 0 of a Riemann sum. That turns into the definite integral. And not only that, but if you look at the expression that I have within the Riemann sum here, I've got a delta y over delta x, so the change in y over the change in x, that's the difference quotient. And as the difference quotient, as the denominator goes to 0, that gives me the derivative. Therefore, the arc length is equal to the integral from a to b, remember the original curve went from a to b, of the square root of 1 plus the derivative of the curve dx. Okay. So this is where your arc length formula comes from. In subsequent videos, I'll do examples of computing arc lengths. In this one, I just wanted to show you where it comes from. Thanks for watching. Please consider subscribing.